Okay, so we're on the last page of the wireless problems. For this first one, I'm going to do a little bit of math to start, and then I'm going to use that to do all of these problems. So for everything except for FSK, frequency shift keying, our equation for bandwidth is bandwidth equals 2RB, the bit rate, over N. So for this, in this case, we're saying the transmission is bandwidth limited to 200 kilohertz. So we're given bandwidth of 200 kHz equals 2RB over N. So we can, sort of mess with this a little bit, finesse it and say that 200 kHz times N equals 2RB. And then we get that RB is equal to 100 kHz times N. Okay, so we're just working the bandwidth equation because we're being given that number to then find out what RB is, and that's going to be the same for all of these. So the only thing that's going to change is our N for whatever the N is for this. And you can have that N from the equation sheet that's given in chapter 22, I believe. There's a big chart at the end that says N for each of these types of digital modulation. You should have that written down somewhere or know how to derive it, how to figure it out. Okay, so for on-off keying, on and off are our two states. So N equals 1. That means that our 2 times, or our RB is 100 kilohertz times N. N is 1, so it's 100 kbps. When we convert to bit rate, we move from kilohertz to bits per second, or hertz to bits per second, and then kilohertz to kilobits per second. Amplitude shift keying, in the case that we don't have anything telling us that we're using more than 2 different amplitudes, ASK is also N of 1. So here we are using the same equation, 100 kilobits per second. BPSK, binary phase shift keying, and so again, N equals 1, which means that we have 100 kbps. 64 PSK, so now it gets interesting. So N equals log base 2 of M. M in this case is 64, so log base 2 of 64 means that N is equal to 6, which means that then if we use RB equals 100 kilohertz times N, that means that we have 600 kbps. Same thing for this one, N equals log 2 of 1024, which is going to be 10, which means we have 1000 kbps, or if you want to be fancy, 1 megabit per second. Okay, so this one is, again, just using that bandwidth relation to bit rate equation and finessing it to have the bit rate come out each time we know N. And N is the only thing that's changing here. Okay, number 17, what are the 2 conditions required for successful jamming to occur? So same frequency is the first one, and we need to have jamming power greater than the target signal power. Really, we need a JS ratio greater than 1, because JS is actually including a little bit more like the EIRPs. Okay, next part. If a bad guy receives antenna, or if the bad guy receiver antenna is directional and has a beam width of 15 degrees, and your jamming EIRP is equal to the bad guy transmitter's EIRP, where is the best place to position your jammer? Put an X in the geography diagram below. This is a very precise diagram here, of course. The main detail here is that there's a very small beam width of 15 degrees. That means that if we are not directly in line with this, if we're even 15 degrees off, we are losing half of the signal power. Since our EIRP is equal to the bad guy's EIRP, we know from the sort of jamming equation, JS is equal to EIRP of the jamming signal over EIRP of the signal that we're targeting, and that gets multiplied by the distance, the original signal squared over the distance to the jamming signal squared. So what this tells us is that if we want to make sure that EIRP doesn't change. If we are out of the beam, we are going to have a lower EIRP. So we have to be directly in line with the receiver from where the transmitter is coming so that we are in that directional beam to jam the signal. And we want to make sure that because our powers are equal, that's going to be 1 times the distance to the original signal squared over the distance to the jamming signal squared, which means we want our jamming signal to be closer to the bad guy than the bad guy transmitter is, so we maybe want to be somewhere in between. So this is the answer is basically just, X marks the spot. We want to be between the receiver and the transmitter so that we are closer to it. If we are further, then we're going to have a less than 1 ratio instead of the greater than 1 that we need to have successful jamming. Okay, on to the last problem. So you can do this one in 2 different ways. Again, the solution online shows how to do it with decibels. So I'm going to do it with watts instead. It's helpful probably to try to do it both ways. Make sure you understand both equations. So what I'm going to use is the same equation from the last one, which is JS equals EIRP of the jamming signal over EIRP of the signal we're targeting times the DS squared, distance to the original signal squared, over DJ squared, distance to the jammer. In this case, we can convert the EIRP of the signal transmitter. So signal transmitter EIRP is 14.5 dB watts. So EIRP of the signal is 10 to the 14.5 over 10. And this is going to be in watts. And that is approximately 28.2 watts. So our EIRP of the signal is 28.2. We can then figure out what EIRP of J over EIRP of S is because we're given that jammer EIRP is 44 watts. So 44 watts over 28.2 watts is the EIRP part of this. We are also given that we are located at 5,500 meters, so that's distance to the jammer, 5,500 squared. And then the signal that we're jamming originates from 3,000 meters, so those are the 2 distances. So 3,000 squared is on top there. And if we plug this into a calculator, we're going to get that the ratio is approximately 0.46. 0.46 is less than 1. So jamming is ineffective. Should have given him the raspberry. Anyways, good luck on the exam, and see you on Wednesday.